Okay, so we've all seen them, right? Those absolutely jaw-dropping images from the James Webb Space Telescope. But today, we're going to pull back the curtain, because the most important stories that Webb has to tell, well, they aren't actually in the pictures themselves. You see, JWST's real superpower isn't just taking these gorgeous photos. It's about revealing secrets that are literally invisible, secrets that are encoded in the light that's traveled for millions, sometimes billions of years, just to reach us. And thanks to its insane sensitivity, Webb isn't just looking at the stuff we already know, like stars and galaxies. No, it's opening up brand new windows, letting us peek into these chemically rich, super complex environments that, honestly, we've never been able to study like this before. And the places we're looking at are just wild. We're talking about the hazy clouds around comets, the thick, soupy atmosphere of Saturn's moon Titan, the air on planets orbiting other stars, and even these superheated cosmic nurseries called interstellar hot cores. Every single one is its own little chemical laboratory floating out in space. Now, this is where it gets really interesting. That light coming from these places, it's not just for making a pretty picture. It's pure data. You should think of it like a coded message sent by molecules from trillions of miles away. And our job is to figure out how to read it. And the tool we use for that is called spectroscopy. It's actually a really cool idea. Just like every person has a unique fingerprint, every single molecule out there has its own unique light fingerprint. By breaking down the light and looking at these chemical fingerprints, we can tell exactly what these distant places are made of.
But, and this is a big but, cracking these codes is way harder than it sounds. Why? Because these places are often totally chaotic, and the molecules inside them, well, they don't exactly play by the rules.
As astrophysicist Francesca Tornolo puts it, the molecules in these places are often in a state of non-local thermodynamic equilibrium. It's a mouthful, I know, but all it really means is that they're out of balance. They're being constantly energized in all sorts of crazy ways, and that completely messes with their fingerprints, making them really, really hard to read. And the difference is just huge. So picture this. In a calm, simple environment, a molecule's energy is basically set by the temperature around it. Nice and simple. But in these complex places JWST is seeing, oh no, it's a constant, chaotic tug-of-war, where a molecule is getting blasted by radiation and smacked around by other molecules all at the same time. So here's the bottom line. If we want to read that message correctly, we have to understand the bumps. We need to know exactly what's happening during those tiny quantum-level collisions. They are the missing piece of our cosmic translation key. And this has created a pretty urgent problem. We are getting a fire hose of incredible data from Webb, but our scientific translation key is full of holes. It's kind of like being handed a whole library of books written in a language we only partly understand. So right now, physicists are in a desperate race against the data itself. And that race is really focused on two major fronts, two massive gaps in our knowledge that we've got to fill, and fast. So first, we just don't have enough data on what happens when molecules bump into heavier particles. Think a pinball hitting another pinball versus a pinball hitting a bowling ball. Totally different outcomes. And second, we're seeing a whole new kind of molecular wobble that only an instrument as sensitive as Webb can even detect. You see, for decades, pretty much all of our models have been built around collisions with the two most common things in the entire universe, molecular hydrogen and helium. They're the lightweights, the usual suspects. Our databases are packed with info on them. But is that really good enough for these new, super complex places that Webb is showing us? I mean, what happens when a bunch of other, heavier molecules get in on the action? Yeah, the answer is a hard no. In places like comets or planetary atmospheres, the molecules we're trying to study are smashing into heavyweights like water, nitrogen, and carbon dioxide. And it turns out those kinds of collisions change everything. And I mean, the difference is just staggering. Look at this. If you try to just substitute the data for a simple hydrogen collision when you should be using the data for a water collision, you get it completely wrong. We're talking about being off by a factor of 8. An error that big means you would totally misread the message from space. That second gap is just as big a deal. Webb's infrared vision is so powerful, it can see molecules not just spinning, but also vibrating, kind of like a tiny wobbling spring. This is a brand new frontier. It lets us study molecules like carbon dioxide that we couldn't really see before, but only if we have the right collision data to understand what those wobbles mean. So how on earth do you fill these huge data gaps? I mean, you can't just fly out there and watch the molecules bump into each other. So instead, scientists are on this high-tech data hunt, using massive supercomputers to basically simulate the universe, one collision at a time.
They're called quantum scattering calculations, and it is mind-bendingly complex work. Scientists are essentially using the fundamental laws of physics to simulate every single possible angle, speed, and outcome of two molecules colliding. They run millions and millions of these virtual experiments to generate the exact data they need to complete our translation key.
But even with supercomputers, there's a trade-off. The super-accurate, gold-standard methods take forever and cost a ton of computing power. So to keep up with the flood of data from Webb, physicists often have to use these clever approximations that are way faster, but just a little less precise. It's this constant balancing act between getting it perfect and getting it done.
Okay, so we've been deep in the weeds of molecular physics. Why does solving this tiny microscopic puzzle matter so much? Because it turns out understanding these little bumps is the only way we can unlock some of the biggest answers in all of astronomy. When we get the collision data right, we can finally read the chemical history hidden inside of comets, which tells us how our own solar system was born. We can decipher the clues in Titan's atmosphere that might tell us what a young Earth was like. And, maybe most exciting of all, we can figure out what the conditions are really like on planets orbiting distant stars.
And really, that's the whole story right there. All of those breathtaking, goosebump-inducing images and discoveries we get from Webb, they are all built on a foundation of incredibly difficult and, let's be honest, often unsung molecular physics. To see the big picture, you have to solve the smallest puzzles first.
This whole scientific quest to build the perfect translation key, it's not just about numbers. It's about making sure that when the universe sends us its next great story, we're actually able to read it. Which really makes you wonder, what other cosmic secrets are just sitting out there waiting for us to find